As part of filters in power supplies, the first filter we're going to see in this video is L filter, inductor filter. So in place of this filter block here, we'll have a inductor filter placed. Here the filter place we have inductor, which is in series with the load resistor. Now at the output of the rectifier we have AC component plus DC component. Now we know for DC input, inductor acts as short circuit. Hence, whatever is the DC voltage that is coming out of the rectifier would get dropped directly across the load resistor, and no voltage drop of any sort across the inductor because it's a short circuit for DC. Hence, we can write all of DC drops across the load resistor RL. Now coming to AC, obviously the reactance that we would see because of inductor would be J omega L, and resistor obviously is RL. Now inductor and load resistor in series will be like a voltage divider. So now the AC voltage would get dropped across inductor some part, and some part would get dropped across load resistor. Now both inductor and resistor in series would act like a voltage divider. And obviously we want the AC voltage to be dropping most of it across inductor, not across the load resistor, so that we get DC directly to RL and no AC at all. But then we need to have that the reactance we have, that is omega L, the magnitude of it, should be very greater than the load resistor, so that when AC voltage is coming, that gets dropped most of it across the inductor, not across the load resistor. So pictorially, let me represent that DC directly goes to load resistor, but depending on how much is the inductance value and load resistor value, AC would get dropped across inductor and load resistor. Now to understand this in even more detail, let me model the rectifier output voltage by using the Fourier series expansion we have seen in the previous video, where the output of the rectifier for a full wave rectifier, let's say, is 2 Vm by pi minus 4 Vm by 3 pi cos 2 omega naught t. And let's neglect the 4 omega naught term and so on and so forth, because the magnitude reduces very fast. So let's concentrate only on the 2 omega naught term here as AC component. Now the output of the rectifier can be modeled like this, where I'm going to show the AC component, which is this value. The AC source is 4 Vm by 3 pi cos 2 omega naught t. Of course it's a minus sign. And the DC voltage we have is 2 Vm by pi. So this is the output of the rectifier. Now let's connect this through the inductor and the load resistor. Ripple factor is given by RMS value of AC component at the output divided by the DC component at the output. Now we know what is the DC component at the output, because if you look at the DC value here, this gets dropped directly across the load resistor, because for DC the inductor is short circuit. Hence we know what is the DC component at the output. But let me write this in terms of current. This is I dash RMS, we have seen earlier, and this is IDC. Now as we have just discussed, we know what is IDC, which is equal to VDC over RL, which is equal to 2 Vm by pi times RL. This is equal to 2 times Im over pi. This is IDC value. Now all we need to find out is I dash RMS, which means we need to find what is the AC component across the load resistor. So for that, let me say that IAC component that is flowing through the circuit will be equal to VAC over the impedance seen by the AC source, that will be equal to XL plus RL, and this can be approximated to VAC over XL, because we assumed that omega L is very greater than RL. So with that assumption that magnitude of XL is very greater than RL. Now in order to find I dash RMS, we need to know what is the peak value of the AC component present across load resistor. So in order to find that, we need to find what is the peak value of IAC. So IAC peak will be equal to VAC peak over magnitude of XL. So now we know what is IAC peak. So hence we can write that I dash RMS is equal to IAC peak over square root 2. Because as this is a full sinusoid kind of a wave, full swing having both positive and negative part of the wave, hence the RMS value will be peak value divided by square root 2. Now we can write I dash RMS is equal to, we know what is IAC peak, which is VAC peak by magnitude of XL. So VAC peak, we know that comes from here. This is the value. When we take the magnitude, we get 4 Vm over 3 pi divided by magnitude of XL times square root 2. Now obviously magnitude of XL is omega L, but omega is the frequency at which it is operating. We know that omega is 2 omega naught because the frequency of the sinusoid waveform or cosinusoid waveform is 2 omega naught. Hence when we substitute that, we get 4 Vm over 3 pi square root 2 times 2 omega naught times L. So we can cancel this 2, we can cancel even this 2 with the square root, hence we get a square root here. So the resultant value I dash RMS would be equal to square root 2 Vm over 3 pi omega naught L. And you have to remember that omega naught is the input main supply frequency. Now knowing both the values, we can write what is ripple factor, which is equal to I dash RMS is found here, that is square root 2 Vm over 3 pi omega naught L divided by the IDC is equal to 2 Vm over pi RL. So we can write the ripple factor is equal to Vm cancel, pi cancel, square root 2, when we cancel here we get square root 2 here. So the ripple factor is RL over 3 square root 2 omega naught L. This was derived under one assumption, that is magnitude of XL is very greater than RL. And looking at the ripple factor, we can say one thing, that is we should use the inductor filter when the load resistor is very small, so that we get ripple factor to be small. So inductor filter should be used when load resistor is smaller, or in other words we can say when the load current is larger. If you like the video, please give a thumbs up. If you haven't subscribed yet, please do subscribe, and thank you for watching.